Hello, I'm Umnik. I will be solving the first educational round and trying to explain what I'm doing. In problem A, we asked if some number n can be represented as 2 times x plus k times y for given number k and non-negative x and y. So all even n's can be represented, and if k is odd, then all odd numbers that are at least k can be represented and all smaller can't. Why is this a problem? But okay, sure. Problem B, we have some infinite grid, some kind of flags. Okay, so legs describes the length of the jump. So initially we can perform some operations. Jump by x coordinate in the positive direction, jump by y coordinate in the positive direction, and increase length by 1. We asked what's the smallest number of moves to reach cell AB. It looks like some kind of square problem. A and B up to 1 billion. We have 100 tests. The coordinates are almost independent, and so if we let's fix the number of times, so we'll do the third operation, so m++. If we will do it k times, then at some moments of time we will have jumps of length 1, 2, 3, and so on up to k plus 1. And we can, between those increases, we can do jumps of that length by both x and y coordinate. So we if we try some number k, then we just need to represent given a and b as a sum of minimum number of summands. All of them are up to k plus 1, which is just a divided by k plus 1 rounded up. And so the answer for given k will be just k plus a divided by k plus 1 rounded up plus b divided by k plus 1 rounded up. And we can see that if we set k to be like 10 to the fifth, like it's something like square root of this number, then like all three summands k, a divided by k plus 1 and b divided by k plus 1, they will be all around square root of 10 to the ninth, so the answer cannot be greater than 3 times square root, or like well, 3 times square root is a reasonable bound. We don't need exact bound. We can just say that okay, the answer is always at most 3 times square root 10 to the ninth, which is not very big, and it doesn't make sense to make k bigger than that because we have k in answer, so if k is bigger than 3 square root of 10 to the ninth, that is already worse than the answer we know that we can get. So we just iterate over k up to like 200,000 and update the answer. Actually, we will not put this constant there. We can just like stop iterating if k is greater than current optimal answer, because we know that we will not improve on it anymore. It's integer, but like I will try to calculate the sum of 3 numbers. It cannot be greater than like bound of long because like one of those numbers is k and it is at most square root of 10 to the ninth power, so it's like 2 times 10 to the ninth plus something small which fits in integer, but like it's better to do it in long because why not? Long statement. Okay, so we have n boxes. In each box there are infinitely many balls of color I. We need to get ball of specific color somehow. For that purpose we have bought 2 robots. I guess the program for each robot is a list of indices, and in those 2 lists every index should appear exactly once, so we like distribute system. That first robot is responsible for some list of boxes, and the second robot is responsible for some other list of boxes. I don't know if the order is important yet. If we request color X, each robot looks through the boxes that were assigned in the order they appear in the list, so the order is important. The first robot spends S1 seconds analyzing, the second spends S2 seconds analyzing the box. As soon as one of the robots finds the box with both of color X and analyzes its contents, the search ends. Search time is the number of seconds until that happens. So it's just like position in the list in which number X is multiplied by S corresponding to that list. Okay. Okay, so we know the frequencies of requests. So it is kind of like encoding task. Like we need to construct kind of encoding, but our encoding is very very special. So like we assign a robot and the index. Okay, so if some color X is in case list on position I, for all requests of that color, we will spend, like for each request, we will spend sk times I. So, and we do that rx times. So we need to assign different values of pair ki to each ball, and for each pair ki we know the cost of one operation with that, which is sk times I. So we will choose n cheapest operations and just use them, and then the problem is like to match two sequences of positive numbers such that the sum of like corresponding products is minimum. That's rearrangement inequality. You just need to assign the smallest number to the smallest to the biggest. Sort them in opposite order. That works because like we will not create empty spaces in the lists we are constructing, because the earlier the position we use, the cheaper is the operation, so it doesn't make sense to use more expensive operations. that's it. I would say. Actually, like, it is possible to do the same with more than 2 robots. Like, just greedily take minimum value from each one. Well, it's a bit harder, but not by a lot. So for each robot and position in its list, we need to add an option to take this robot, this position, with the corresponding cost. The corresponding cost is the cost for one step of this robot multiplied by position, which should be one indexed. And I will take the cheapest of them, so I need to sort by that cost, and here I will just put like the identification of that position. So items are sorted in decreasing order of the values. So I will just go and match them. I don't actually need this. Because I know that options here are sorted by value, so inside for each robot the relative order is the same as relative order of positions in the array. So actually I didn't even need to store them. Now I will just say like for a robot which is the next option, which ID is written here, we should put the corresponding position of our box in their answer. Is it my internet issue or Cadfors issue? Looked like my internet issue. Okay, let's just move on. So in problem D, I have n items. For each of them we know value f and value d, but value d we can change. And values f we cannot change. So for item I, we know fi and current di that we can change. The integers, then pi is calculated as a product of fi and di, and we want to make all of pi values to be in some range of length k. So the maximum of them minus minimum of them should be at most k, where k is a given value and it is rather small. And values f are also not that big. We can change some di's. They still should be integers that are strictly positive, and we want minimum number of di's changed. Is it like always possible to, if I can change all of them? Well, yeah, I guess I can make all of p to be equal to like 2000 factorial by saying that corresponding di is 2000 factorial divided by fi. It is always divisible, we will get a positive integer, so yeah, I can change all of them if I want. If there is some position that I will not change, then my segment should be kind of very close to that number, to like initial value of pi for that I. So if I fix left border of a segment, for example, I will know the right border. And thus let like for each I will just check if current value is okay, then we shouldn't change anything, and then just check if some value is fine for us. Okay, that would work in like n times k, like k plus 1, because for fixed I there are k plus 1 possible left borders such that current value of p is inside those borders. And then check all the n options. That's n squared k. That's not good. But if I only fix index of the one I don't want to change, then for all others I want to be either the closest value on the left or the closest value on the right, so I can find those values. And now I need to check if I okay, let's draw something. So let's say that I is not changed, then like there is this point gi times fi. I will need to choose some segment of length k, and like for every j so like if this is in the segment it's just good, it costs 0. Otherwise like there will be so we have f, and we can get numbers that are on distances f to each other, and either this one will be inside the segment or this one inside the segment, or like nothing is inside the segment. So for j we can get those positions lj and rj. So like let's say that if this is x, then we should have x between L and R. So we can say that R minus x is some parameter that we can choose. It's called t, then t is from 0 to k. And then like for given j, for each value t, we can kind of determine what will be the cost for this j. So like some t's are just good right away, like this number lies inside the segment. So for such values t, we can just say that they're good. like it should be kind of should be simple, right? So here's our x. This is t, so x plus t is r. So this will be k minus t, that's L. And for given j, there is some positions that we can get for free. And there are also like leftmost and rightmost neighbors, which we like if they're inside of segments, then we pay 1 because we will need to change d, but it is possible. Okay. So to have this one side, like this, let's say that this position is A, this position is B, this position is C. Then we know that B is non-negative, and like it is good if T is at least B. C is non-positive, and we will be good if K minus T is at least minus C, which means that T is at most K plus C. Okay, so if we draw like possible values of T, so we have 0 and K, we have to be somewhere here. So for A, it can be either one of those cases, but that just means that like, so this is some suffix of values of T, this is some prefix of values of T. So for A, like on this picture, for example, we will say that here we can get it for free. Then for B, it will be some suffix which is bigger, and for C, it will be some prefix. So we will say that this segment is just bad, because if we choose T from this segment, then we will just not be able to choose corresponding value of D. Yeah, and so let's say that we want to calculate cost for every point. So like on this segment we will add plus infinity. On this prefix we will add plus 1. On this segment we will add plus 1. And this segment we can get for free. So we just have constant number of updates. Since K is small in this problem, we can just have an array of lengths K plus 1 and do the, well, we kind of want to use prefix sums to add on segment of line. So since K is small, we can just do it on an array of size K plus 1. But actually we can just like remember all the points in which we want to do updates. and get a solution in n square log. Okay, this won't be nice to implement, but let's do that. I will implement the n square log solution. It's worse in these constraints, but it is like doesn't depend on k being small. So from initial values of D, we are only interested in the initial product. So let's just multiply them by F, and I will call them A because it's just a number. Okay, we can always get N. Otherwise, like to get something smaller, we have to keep at least one of the numbers. So I want to have like function of cost, cost of setting t to some value. It is initially like infinity for negative values, then from 0 to k inclusive it should be 0, and then infinity for values strictly greater than k. So I will just remember that my initial value is infinity. Infinity will be n because I'm not interested in answers that are greater than my n. So my initial value is infinity, but in point 0 I need to decrease by infinity, but in point k plus 1 I need to increase it back by infinity. And now for all the items, I will check like if their initial value is near x. I need to carefully say that it's 0 there. Otherwise I will find closest to the left and to the right, and just say that it's 1 on like for values of t that well, like here, like it should be +1 for those segments and plus infinity between them. If x is equal to ai, then any possible t will be for free. So it's just like add 0 everywhere that it matters, and that is done by just doing absolutely nothing for that item. Okay, so otherwise, so I want to find this point and this point, like from where I can get something. So I need to find closest multiple of fi to x on the left and on the right. So on the left it will be x divided by fi multiplied by fi. That's just L, right? I mean that's position of L, so the actual that's the position of the closest to the left point. The corresponding value of so it's here. So like value of like if t is very small, like if t is 0, then it is probably covered, and then when I increase t it will stop, like the biggest value of t when it is covered is like if k minus t is equal to x minus the position of the element. So t is k plus z minus x. Okay, then on the right, like the next point is bigger by fi, and similarly, so the smallest t when it will be covered is when t is equal to z minus x. So if L is L plus 1 is at least R, that means that for every value of t I can do something. So I can say that everything is good. Like L is k and L is k plus 1, for example. Okay, so now like on segment from 0 to L I should add plus 1. On segment from R to K I should add 1. Between them I should add plus infinity, but also there can be a zone where it is 0 actually. Yeah, it is not very clean. So this is the case when there is a zone when it is 0 and it is a suffix. Here it is a prefix, and here there is no such zone. So this should be an easy case. I should just say that in 0 I should add 1. Then in L plus 1 I should add n minus 1. So like, I mean, it is infinity there, but it is already infinity there, so it doesn't matter. So 0, then 1, then n, then from R it should be 1 again. So like in point R it should be possible to do it easier. I can just say that I do this always. Like I will have a starting value. So I start with n, then minus n, I'll get 0, then n. And here I just like start with 1. So I increase core value by 1. Then at infinity, then well, I can just at infinity. Then subtract infinity back in point r. And I can do that always. But also here I'm saying that like there is initial value for which I should pay 0, but it is a valid option, so I should have added 1 there. Instead I should add 0. That is done by subtracting 1 on some segment. So here I should probably subtract 1. It's greater than x, so it should be like this. It's ai minus x. Subtract 1 there, and then in k plus 1 I add it back. And here it should be like left border here. Subtract 1 in 0 and then add it back at k plus ai minus x plus 1. Amazing solution. Okay, but now it is easy. So sort all the events, all the changes that we need to do, and just run left to right, do the updates, and if from this event, we will go further. Then it means that I have made all the updates in this point, so I can update the answer now. If it won't work, it will be super sad. And it also can be slow. Amazing. Something bad happened. Great. Oh no. Yeah, there can be. Yeah, I remembered about that, but then forgot when I wrote it. So, yeah. Here we can have 0, which is not a valid option actually. What should we do in that case? Oh. So this I can do always. Right, so this actually can be done just here. That's always okay. Otherwise, if that is 0 here, then we need to do something special. Well, that just means that like from everything that is strictly smaller than r is actually very bad. So we just like say like here, and in r we just add minus n. Well, let's submit first, and then I will probably have to write stress test or something. I will read it once and then probably write a stress test. But honestly, like at this point, I should just move to the next problem. This is so bad. very small, I have to add at least this for to be valid right border, because left border should be at least one. I don't know, kind of looks okay. But apparently something's wrong. D is under investigation. Okay. Let's just move on. You are given an undirected graph consisting of n vertices and n minus 1 edges, but it can be not connected. Oh, it's a bamboo. Okay, so not only it's a tree, it's a bamboo. Okay, so we have a bamboo, and its edge has weight vi. Each vertex contains a chip. On each chip there is a number on the chip that is initially in each vertex is I. Apparently we can do some operations. We can choose any chip and move it along one of the edges. The cost is the weight of the edge. The cost of the graph is minimum cost of sequence operations. That means the following conditions. After all operations are performed, every vertex contains exactly one chip, and the integer on the chip is not equal to the index of the vertex where the chip is located. So we need to construct some what's called derangement of minimum cost. Okay. Okay, so in the end, like we will have some permutation. So like there is a let's draw an edge that means that like we took a chip from first vertex and it end up in here, for example, from fourth end up in third, first, something like that. So if we fix this permutation, what is the cost to achieve that? Well, for each chip, it should traverse all the edges that constitute this path. So for each edge, we will pay for it that many times, how many times it some edge goes we said like along this small edge. In our permutation, there can't be cycles of length 1 because that means that the chip stayed at the same place. So all the cycles should be of length more than 1. That means that for some vertex there should be at least one edge that is neighboring to it that was used, right? Because otherwise it means that there can't be any edges that go from this vertex to the left or to the right. So we should have something like this. So for each vertex there should be, like here we have 0 and all other edges are used. Each edge will be used even number of times because how many chips moved from left to right, the same number of chips, like we have freed some positions on the left, so the same number of chips should move from the right to the left. So all of these like non-zeros are at least 2. Okay, but now I say that for any configuration of edges such that there is no isolated vertices and each of them is chosen 2 times, we can construct corresponding permutation. And it is kind of easy, like we have those chains and we need to draw just cycles that like doesn't move back and forth, just like one cyclic shift will be good, and this will move each chip from its initial position somewhere else. So basically the problem that we asked to solve is we're given an array of n-1 integers. We have to choose some of them. The cost will be 2 times sum of chosen numbers. We want to minimize the cost. Right. And it is not allowed to not choose 2 consecutive numbers. And also we have to choose the first and the last number. Well, that sounds like DP problem, but we also have some updates. We have updates of the cost. Well, it seems that we should just take calculation of this DP and put it in segment tree. So we can build a segment tree over our array, and in the node of segment tree we will store like what is the cheapest way to choose something valid, but for like two bordering values we explicitly store do we choose them or not. So we will store like 4 values for whether we do not choose both borders, but that means that we have to choose like the next value there. You need to be careful with initializing, but okay. Yeah, that won't be nice. Okay, fine. Well, we like choose this one, but not this one. But that means that we have to choose the neighbor, not this one, but this one. And here we have to choose the neighbor and just choose both borders. And in such segment tree, we can merge two. We can merge two such DPs. We will iterate over what is like on the border where they connect. It is not allowed to not choose here and also not choose here. And just choose the best value, I guess. Yeah. Well, okay. I have segment 3 pre-written. Right, so I need to define what do I store in segment 3. In segment 3 I will store 4 values. How to initialize for a segment of size 1? we can not take it for free, or we can take it. This way we'll take both bordering elements for this cost, and other options are not viable. Okay, so to merge two elements, okay, this is not good. Like I need to make sure that I always apply left is this and right is this, because like it matters here. Or I can just like write operator plus like normal person. So we want to merge two DP segments, and values for borders are x, I, j, y. I and j cannot be 0 at the same time, because that means that there are two elements that we didn't choose in the middle. So we have this, and in the end we'll have x and y on the borders, and we should update it with axi plus okay. I do not need this. Yeah, and I cannot write it like this. This should compile. Cool. So now it should be super easy, right? I don't actually need this. Can we just send t? That's an interesting bug. Okay. Alright. I'm incorrectly merging empty sync. Yeah, okay. Guess guess I need to like explicitly say that if not active, return the other one. If it is not active, then just return this. Otherwise, actually merge them. That should be okay, but it isn't. And here I should say that it is active. And multiply by 2. That one I can understand. It's so nice to have pre-written segment tree. I'm not used to it. Yay, G accepted. Okay. Have half an hour. Problem F. So there is an undirected graph. For each vertex we have some segment of accepted frequencies, whatever that means. Tower B is accessible from tower A if there exists a frequency X where consecutive towers in the sequence are directly connected by wire and each of them accepts frequency X. So there should be like a path from A to B such that intersection of their segments is non-empty. Accessibility is not transitive. Your task is to determine the towers that are accessible from the first tower. I'm tempted to do like scanline by frequency, and then we when at frequency x there are some vertices that can accept the frequency x and other vertices cannot accept frequency x, and so so we have for each x there will be some graph, like we remove the vertices that are bad, and we should look at the connected component of first vertex and say that everything in that connected component is kind of good. Well, it looks like cross-color reachability 3 on like dynamic connectivity offline. So we do scanline by x, but instead of doing scanline by x, we'll actually like build the segment 3 on x, and we'll do DFS on that 3. Oh my god. Well, okay, that is what is written in this file. Okay, so like there is dynamic connectivity offline problem that basically does what we need to do, like with the scanline by X. Um, so at some point we have to turn the vertex on, then turn it off, and that's it. So like each vertex exists on some segment of axis. We want to kind of look at the connectivity of the graph at every x. So that means like we kind of like for every x we want to turn on the vertices that are on one for this x and look at disjoint set union basically. So to do that we can do divide and conquer. Like, well, it is easier to imagine if we like build a segment tree on axis, then each vertex exists like on segment of axis, so it is on logarithm vertices in that segment tree. Then we do DFS on segment tree, and when we like arrive at vertex, there are some a node at segment tree. There are some vertices that we need to turn on. What does it mean? It means that this vertex will exist for all the axes on the corresponding segment. And when we will reach the end, like when we will reach some leaf that corresponds to number x, we will have DSU that exactly with turned on vertices for this x as we wanted. Okay. So what we will do now? So like for each leaf, we kind of want to say that well, the component in which vertex 1 is now, like everything in that component is good. Okay, so how do we do that? Maybe it's how possible. No, that doesn't sound possible without. So along with DSU, there is like Kruskal reachability tree. If we do DSU, we can like each time we merge something in DSU, we can create new vertex and like connect it to two vertices for the old component. So like we will have this rooted forest where for each vertex of the graph, the path up in that forest is like the sequence of components in which this vertex were in like while we were doing DSU. Yeah. So if we just do DSU, it is a forest. But since we now have like branching timelines, like with DFS on segment 3, and like when we go, like when we return from vertex, we have to remove all the vertices we added there, but they were added last, so we can like undo their addition with stack. And so if we now like try to construct this cross-call reconstruction tree, during that process it will not actually be a tree, because like in different moments of time we can create like different parents for like for component. Like at some moment of time it can be merged with something, but then we will undo all of that, go into the other branch, like in time, kind of other parallel universe, and merge it with something else. So for that merge we'll create a different component, and so like there can be different parents, but we can like look at it as a directed graph, and like at some moment of time, like it is a tree with edges directed up, but we like merged all of them, so it is kind of like persistent structures that stores the tree. And now we want like for all moments of time we want to look at the vertex 1 in the graph and mark all the components in which this vertex existed as good. We can do that with like DFS or like BFS. BFS is better probably. The graph will be kind of big. And then so we mark all the components as good, and now we want for all the vertices of the initial graph again, like check if they were in a good component at some moment of time. Now we can like on the reversed graph like push those marks back to leaves, kind of in this persistent tree thing, and that will mark the vertices we want. It shouldn't actually be like hard to implement, but it also won't be nice to implement. I can say that. Actually, I probably don't need to explicitly construct the graph. I can just calculate everything on the fly. Like I can mark a component as component connecting vertex 1, and when I merge it with something, like I will say for a new component that it contains vertex 1. But then when I destruct component, I will say okay, like this, if this component did not, well, while it exists, it either contains vertex 1 or not, and if it does, then to both components that were merged to create this one, we can say that everything in those components is good. and I should carefully like not undo those actions. Well, in 16 minutes, I'm not sure that I can implement that. But generally, like it doesn't sound that bad. But yeah, I will have a lot of components. Okay, so I will need segment 3 kind of. Like normally when I would write, well, normally I say like I have done it more than 3 times. If I will implement Kruskal reconstruction tree, I will just like create new component every time I merge something and just hang both of the vertices by that. But when I do this U with undos, I cannot do path compression, and so I can have very long passes there. So I will have to not do that. So I will do this U kind of normally, actually like in small arrays, and store the ID of current component, and like those changes okay, so I have rollbacks. Vector is not nice, but whatever. Okay, so I have pushed like in segment tree style, like on set, like say that on this segment this vertex exists. Like this is just segment tree addition. Red graph constructed empty GSU and said that component where vertex 1 is initially has 1. And like run the recursive function that is DFS on segment 3. So after that I will just like print out. Okay, so we'll remember what was the stack size before we entered, and we should add all the vertices that are in this node of segment 3. So like activate X, then if v is less than 10, DFS just like run recursively from the sans in segment 3. Okay, and now we need to deactivate vertices, which is done by removing changes from segment removing changes from the stack while they exist. But like we need to kind of push or we don't. Just undo. Should work, I think, if I do like everything in GSU correctly. So okay, like changes, make change, of v activate of v make 1, run through all the neighbors, and if the neighbor is active, we should try to connect them in DSU. So new ID will be k, and we're just saying that new size is this. New parent of U is V. New ID of V is K. So this, and if one of old components had 1, then then the new component has 1, and also all of them are good. I think that's it. Don't do pass compression. That's incorrect. Yeah, I don't think that I'm pushing enough, but I'm printing more vertices than I should. That is not good. But yeah, I need to push when I'm distracting the vertex. So yeah, that would require more changes in any case. So I can't do it in 1 minute, but like there are some other bugs because the answer for the sample, like I shouldn't add incorrect vertices. I don't really understand how I can incorrect vertices. Well, yeah, yes, I have topological ordering, so you can yeah, I can just push is good after. So yeah, I do this, and I also need to remember that K was constructed from those two components, and now here I just run through them backwards. It works in samples. Oh, it was extended. Then I can submit, yeah. What about mail? Have a lot of memory. Actually, not that lot. That's cool. I haven't seen. Well, this gas crystal reconstruction tree is kind of a new technique. And yeah, I haven't seen it combined with like this with rollbacks, so that instead of just Kruskal reconstruction tree, we can construct like persistent Kruskal reconstruction tree, and it will be like this directed graph. And then we can push some values, calculate dp on that graph as on any directed acyclic graph. That is nice. That is nice. Nice problem. Kind of hardcore contest. But cool. Thanks for watching. Bye.